This is part 6 of the series Quadrilaterals, and in this part we're going to start out with another theorem with rhombi, and it also involves the diagonals. This is the rhombus opposite angles theorem, and it says a parallelogram is a rhombus if and only if each diagonal bisects a pair of opposite angles. What this says is it's a biconditional, and one part says if the diagonals of a parallelogram bisect the opposite angles, then the parallelogram is a rhombus. The other part says if a parallelogram is a rhombus, then the diagonals bisect opposite angles. So to show this theorem, we're going to pick one of those two sides and we're going to prove it, just like we've done in the past with the other theorems. The part of the theorem that we're going to prove here is we have a parallelogram and the diagonals bisect the opposite angles. So AC bisects angle BAD, this angle, and angle BCD, and the other diagonal BD bisects angle ABC and angle ADC. The plan for the proof is I want to show that triangle ABC, this top triangle, is congruent to the bottom triangle, and by so doing I'm going to show that this side is congruent to that side. Because we know that these two sides are congruent since ABCD is a parallelogram and these two sides are congruent, then we'll know that all four sides are congruent to each other, therefore it has to be a rhombus. So that's the plan for our proof. Let's go ahead and give it a shot. So here we have the given that ABCD is a parallelogram, AC bisects BAD and BCD, BD bisects angle ABC and ADC. So our first step is going to be to say that angle 1 is congruent to angle 2. We're using this bisector idea here. So angle 1 is congruent to angle 2. Also, angle 3 is congruent to angle 4. And that's the definition of an angle bisector. Next, we say that AC is congruent to AC. AC is congruent to itself by the reflexive property. You've seen this pattern over and over again. Then, we know now that triangle ABC is congruent to ADC. So triangle ABC is congruent to ADC by angle, side, angle. So we have this angle, this side, this angle, this angle, this side, and that angle. So it's angle, side, angle, angle, side, angle. Now, we do what we intended. We can say that AB is congruent to AD. So AB is congruent to AD. And while we're at it, we can also say that BC is congruent to DC. So BC is congruent to DC. And that's because corresponding parts of congruent triangles are congruent. Now, we say that AB is congruent to CD. AB is congruent to CD because the opposite sides of a parallelogram are congruent, as well as BC is congruent to AD. BC is congruent to AD. Same reason, opposite sides, parallelogram opposite sides theorem. Now that we've got all these congruent statements in here, you should see the pattern in here. AB goes to AD, AD goes to BC, BC goes to DC, DC goes back to AB, and therefore all the segments are congruent to each other. So AB is congruent to BC, which is congruent to CD, which is congruent to AD. That's the transitive property of segment congruence. Then finally, we can say that ABCD is a rhombus because of the definition of a rhombus. A rhombus is a parallelogram with four congruent sides, and here are the four congruent sides. Before we go on to the next property, let's take a little rest and work a quick example. In this example, it tells us that ABCD is a rhombus, and it gives us one angle measure and wants us to find all the other angle measures. And it doesn't really matter where we start here, so let's just pick a place. We know that the diagonals bisect the opposite angles. So this angle and this angle are congruent, and so this angle and this angle are going to be the same as these two. So this angle is 61, angle 3 has to be 61. Let's keep track of the measures here. So measure of angle 3 equals 61. In rhombi, the diagonals are perpendicular, so angle 1 has to be a 90-degree angle. Since this angle is 90, these two angles are complementary. And so if this is 61, then angle 4 has to be the complement of 61, which is 29. So the measure of angle 4 is 29. And we probably should have wrote angle 2 up here as well, because the measure of angle 2 has to be 61 as well, because it's going to be congruent to angle 3. So not too terribly difficult if you know the properties of rhombi. Now let's move on to the next section. Now we've discussed rhombi, we can revisit our chart here, and we see that we have parallelograms and rhombi. Rectangles would be next. So let's start talking about rectangles. This is the rectangle diagonals theorem, which says a parallelogram is a rectangle if and only if its diagonals are congruent. So if the diagonals of a parallelogram are congruent, then the parallelogram is a rectangle. Conversely, if a parallelogram is a rectangle, then its diagonals are congruent. So we're going to pick one of these, and we're going to generate the proof of this theorem. The part of this theorem we're going to prove is we're given a parallelogram ABCD, and the diagonals AC and BD are congruent. And we want to prove that ABCD is a rectangle. The plan for this proof is I want to show that this triangle is congruent to this triangle. We already know that this side is congruent to this, because that was given to us. We're going to use the fact that opposite sides of parallelograms are congruent, and this triangle and this triangle both share side AD. So we're going to show these two triangles are congruent. Then we're going to show that this angle is congruent to this, and this is congruent to this, and because these two triangles are congruent, this angle is congruent to this angle. Therefore, all the other angles are going to be congruent, and this would then be a rectangle. So that's the outline of the proof. Let's go ahead and look at the details. We write our given ABCD is a parallelogram, and AC is congruent to BD. So we have the parallelogram with congruent diagonals. Now, first thing we say AB is congruent to CD. So AB congruent to CD, and that is because parallelogram opposite sides theorem. Opposite sides of a parallelogram are congruent. AD is congruent to itself by the reflexive property of segment congruence. So this is congruent to itself, and now we know that the two triangles are congruent. So triangle ABD is congruent to triangle DCA by side-side congruence. So we had side, 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 side. Now that these two triangles are congruent, I want to say that this angle, BAD, is congruent to angle ADC. So these two lower corner angles are congruent. And they're congruent by CPCTC. Corresponding parts of congruent triangles are congruent. Now we go back to the idea of opposite angles in parallelograms. We know that angle ABC is congruent to angle ADC. So ABC, this angle, is congruent to ADC, this angle, and BAD, this angle, is congruent to BCD, this angle. Because this angle is congruent to this, and this is congruent to this, and this is congruent to this, all four angles are congruent to each other. Therefore, ABCD is a rectangle by the definition of a rectangle. A rectangle is a parallelogram with four congruent angles. Before we move on, let's go ahead and work a quick example. In this example, we have a rectangle QRST. It tells us that QS, one of the diagonals, is 5x minus 31, and RT is 2x plus 11. So based on what we just talked about, in a rectangle, the diagonals are congruent. So let's go ahead and write our equation. We know that 5x minus 31 equals 2x plus 11 because this equals that. Let's subtract the x terms. 3x minus 31 equals 11. We'll add 31, so 3x equals 42. And then we divide by 3. X equals 14. So now that we have 14, we want to substitute it into one of these expressions to get the length of our diagonal. It's not necessary to put it into both, but it's not a bad cross-check to make sure that you didn't make a simple mistake. So we have 2 times 14 plus 11, which is 28, plus 11, which is 39. If we do the same over here, we have 5 times 14 minus 31, which is 70 minus 31, which is 39. So they both work out. So a fairly easy example, but the concept is the important thing, that the diagonals are congruent. So let's move on to the next section. Now that we've worked through the properties of rectangles, we're revisiting our quadrilateral tree again, and we can see that rectangles and rhombi are at the same level, so they both inherit the properties of parallelograms, and those properties are the diagonals bisect each other, opposite angles are congruent, opposite sides are congruent, and consecutive angles are supplementary. That is true for both of these objects. Now, we know that a square has to be both a rectangle and a rhombus, so all the properties of each of these combine into the square. So a square has 4 congruent angles, it has 4 congruent sides, it has all the properties of a parallelogram, it has the properties of a rhombus in that the diagonals bisect opposite angles, and the diagonals are perpendicular, and all the properties of a rectangle in that the diagonals are congruent. So that wraps up this left side of our quadrilateral tree. Now we're going to move on to the right side.